Welcome back. In the last video, we gave our neural networks the power of time and memory using vanilla RNNs. But if you try to use the standard RNN to read a long paragraph or process a long audio clip, it fails completely. It suffers from severe short-term memory loss. By the time it gets to the end of a sentence, it has completely forgotten the beginning. Today we're going to look at the mathematical flaw causing this amnesia, you might say, and the brilliant architecture that fixed it. The long short-term memory network, or the LSTM. Okay, so the problem with vanilla RNNs comes down to one thing: repeated matrix multiplication. So remember backpropagation through time? To send an error signal back 50 time steps, the network has to multiply that gradient by the exact same weight matrix 50 times in a row. If those weights are even slightly smaller than 1, multiplying them repeatedly causes the gradient to shrink exponentially until it hits 0. The signal vanishes and the early layers learn absolutely nothing. On the flip side, if the weights are slightly larger than 1, the gradient explodes towards infinity and crashes your model. We can fix exploding gradients with a blunt trick called gradient clipping, literally just capping the number. But vanishing gradients, that requires a structural overhaul. Here's some good visuals about it. So, to fix this, researchers introduced the LSTM. Instead of just having one simple hidden state carrying all the context, LSTMs introduce a second separate channel called cell state, and it's written as C of T. So it'll be big C and then like a little T right here. I know it's just CT on this screen, but that's how it will actually look. So look at the diagram. The cell state runs straight across the top of the entire module like a conveyor belt almost, or like a uninterrupted memory highway. And information can flow straight down this highway through time with almost no matrix multiplication to degrade it. And this is a secret to preserving long-term memory. But a highway isn't useful unless we can control what gets on and what gets off. To do that, the LSTM uses three highly engineered valves called gates. The first valve is forget gate. Before LSTM adds any new information, it decides what old information is no longer relevant and throws it away. It takes a new input and the previous hidden state, runs them through a sigmoid activation function, and spits out a number between 0 and 1. A 0 means, forget about this completely. And a 1 means keep it exactly as it is. For example, if the network is reading a book and a new character enters the room, the forget gate might decide to erase the memory of the previous room to make space for the new context. Next is input gate. Now, input and output gate. So now what we've kind of cleared out the garbage. What new relevant information should we add to our memory highway? The network calculates potential new memories, and the input gate acts like a filter to decide which of these new memories are actually important enough to get permanently added to the cell state. And then we reach output gate. Our cell state, our deep memory, is fully updated. But we don't necessarily want to output everything we know all at once. The output gates look at our massive memory highway and decides exactly which pieces of information are needed right this second to make our current prediction. That filtered slice of memory becomes our output and also gets passed to the next step as our short-term hidden state. All right, so by separating short-term hidden states from long-term memory highways, LSTMs conquered the vanishing gradient problem and ruled natural language processing for years. But eventually, even LSTMs hit a wall, like when dealing with massive translations and complex context. So next video, we're entering the more modern era. We're going to abandon recurrent networks almost entirely and look at the mechanisms that gave birth to basically ChatGPT and modern AI.